Okay, I think we're good. I will start out. Welcome, everybody, to our 2 o'clock speaker. This is Stephen Kroese. He is a flight engineer at the Jet Propulsion Laboratory. I will also point out that he is a local kid. He's from West Michigan originally. And so it's great to see somebody from this beautiful part of the country go to that beautiful part of the country. And I will note that I'm from Southern California originally, so I'm missing the beautiful sunny mountains today. But Steve, we're so excited to hear your talk, Perseverance Through Adversity, and I'll let you go.
Okay, thank you. Um, yes, I'm a flight software engineer at Jet Propulsion Laboratory here in Pasadena. I've been living in California for about a decade now, and but I am originally from Grand Rapids. I grew up in Grand Rapids. There are only two places that I ever consider my home: Southern California and West Michigan. I got my start writing software in the aerospace industry for Smiths Industries back before they got bought out by GE Aviation. This was back when they were on 44th Street by Roger B. Chaffee Boulevard there. In 2010, I moved out to the Mojave Desert of California to work for a guy named Bert Rutan um, at his company Scaled Composites, and we were building a prototype spaceship for a company called Virgin Galactic, and I did the rocket motor control software for that program. That finished a few years ago, and I was fortunate to have an opportunity, so to speak, to work for JPL, working on the Perseverance rover. At the time, we called it the Mars 2020 mission. And so this talk is going to be a little bit about just what it's like to write software for a nuclear-powered car that drives on another planet, and how we did that during various trials and tribulations of the year 2020. It's been kind of a rough year for everyone, and it took some getting used to, but we, well, persevered through it. First, I'll go over a little bit about the rover itself. This is all kind of in the past. I hope it's still relevant to people, even though the rover did land 2 days ago. This is the spacecraft stack. The top part is the cruise stage. It contains rocket engines that are used during the cruise stage, cruise phase of flight to Mars. It has propellant tanks, solar panels, and some supporting electronics. That gets jettisoned before we entered the atmosphere. I made this presentation like a month ago, so I have to say all this in the past tense now because it's on the ground, and it's amazing. But the next part down, that cone-shaped thing, is the back shell. It protects the rover as it's flying through the atmosphere. Below that is the cruise stage with the rocket motors that lower the rover down to within about 50 feet of the surface. And then the sky crane takes over. The rover is lowered down on these cables. The wheels unfold, and then when it touches the ground, those cables are cut. The descent stage flies away, and we land. The bottom part there is the heat shield that gets jettisoned shortly after the parachute is deployed. The parachute is contained in that little dome part of the back shell at the top there. I don't know if my mouse works. I'll point to it. One thing I would like to point out here is that the cruise stage, the descent stage, and the rover are all controlled by a computer, and that computer is in the rover. The cruise stage and the descent stage do not have their own computers. The computer is in the rover. The rover, you can see there's a little package, a little stowaway on the bottom. That is where the helicopter is. And this is the rover in what we call the Spacecraft Assembly facility at JPL. It's undergoing some mobility testing there. It's hard to describe all the pieces of the rover, so I won't try to do it. But the arm is all folded up in the front there. When it's fully extended, it's 7 feet long. And I learned an interesting fact the other day. All of the instruments on the end of the rover's arm weigh 3 times as much as the original rover that went to Mars, Pathfinder and Sojourner. So just the instruments on the end of that arm weigh 3 times as much as the original rover. That's how far we've come. That coffee can-like thing in the back there is the UHF antenna. That's mostly how we communicate with the rover. The rover in the SAF is in a phase of development we call ATLO, which stands for Assembly, Test, Launch, and Operations. Spacecraft at JPL spends most of its time in the ATLO phase. I like the acronyms ATLO and SAF because they actually mean something. JPL, more than any other organization that I've worked for, is crazy about acronyms and initialisms, and they don't define them half the time, and it drives me bananas. The very name JPL doesn't make any sense, right? I mean, never has the Jet Propulsion Laboratory ever worked on jet engines. Um, the way that name came about is in the late 1930s, a bunch of rogue Caltech students wanted to experiment with rockets. And they were hoping to get some funding, some federal funding and other sources for those rocket experiments, but they didn't want to go around telling people they were a rocket propulsion lab because back in those days, rockets were considered fanciful things and you got mocked for it, you know, Buck Rogers kind of stuff. They didn't take it seriously. So they lied. They said they were a jet propulsion laboratory instead. It's not much of a lie. I mean, it's the same principle as far as physics goes. But the name stuck. It worked. They got their funding. Ironically, JPL no longer does booster rocket development. There are better NASA facilities for that sort of thing. But nobody feels like changing the name because it didn't even make any sense in the first place. So here we are, the helicopter team in their clean room. We don't dress like this specifically for coronavirus. This is how they always dress when they're putting spacecraft together. And that's mostly to protect the spacecraft, not just from dust and dirt and things, but from Earth germs. We take the idea very seriously that we do not want to contaminate our space hardware because the last thing we want to do is discover life on Mars and then find out we brought it there ourselves. That would be an epic disaster. So that's the helicopter team, and the helicopter you can see in the front there. Here's a bottom view of the rover. You can see the helicopter is kind of bolted onto the bottom there. You can see the blades, those carbon fiber blades. They're about 4 feet in length, all folded up down there. The wheels of the rover are covered in this protective covering that will get removed before launch. You can see in the back here these radiator-like things. That's the structure that the RTG goes into. The RTG is the power supply for the rover. An RTG is a radioisotope thermoelectric generator, and I'll talk a little bit more about that later. Here you can see the rover mounted in the back shell. The rocket engines of the descent stage are covered in red covers there. Those will get removed before launch, and then the wheel covers too. That lumpy thing at the top there is the cover over the helicopter. And this is a artist's rendition of Perseverance driving, and the name of the helicopter is Ingenuity, and it must be fun to be an artist for NASA. You can create all these imaginary things. The helicopter is not going to scout out ahead of the rover and look for places for it to drive, at least not on this mission. That may be a future objective, but for this mission, it's what we call a technology demonstrator. The helicopter, we're hoping to get it to fly maybe half a dozen times at the most. It would be an enormous success if we could do that. It flies for 90 seconds at a time. And it's only going to get to an altitude of, I don't know, 20 or 30 feet or so. So it's a proof of concept kind of a thing. Don't expect the helicopter to fly for at least a month. We've got a lot of work to do before we get to that phase. First of all, the rover has to find a flat place to drop the helicopter off. Everything happens kind of slowly on Mars. There's a long process of things that has to happen. The rover has to maneuver into place, and then it has to jettison the cover over the helicopter, and then it has to move away from the cover, and then the helicopter has to drop down, and then I think the helicopter spends a day or two just charging its batteries from the solar panel that's on top of it. Here's the inside of the rover. Makes me remember when I was a kid, I used to volunteer to untangle the Christmas tree lights every Christmas, and I don't do that anymore. I can't stand cabling anymore. Kudos to the people that put this together. All of the computers and the I/O modules and various different components are all buried in there, all mounted to something we call the ramp, the Rover Avionics mounting plate. I have a funny story about some crossed wires that I'll talk about at the end here. As far as what I do, there are about 30 flight software engineers working on the Perseverance rover. Well, we're now starting to transition onto other projects, but at its peak, I think there were about 30. And as far as I can tell, software people, flight software people fall into one of four categories. These are not official categories at JPL, but it's just my observation that this is what people they do what they like to do, what they're interested in. So the robotics experts, these are people that have specialized knowledge about physical mechanisms, the wheels, the mast, the arm. The sample caching assembly is an extremely complex piece of machinery inside the rover that is designed to take samples, run some tests on them, store them away inside the belly of the rover. It's really an amazing machine. And they work on the drills and the actuators and stuff too. There's a group of people that work on the instruments. There's software that interfaces to all the scientific instruments, and this software is used to command those instruments to do their work and also collect the data that is produced by these instruments. And this data is packaged up into things we call data products, and I'll talk about that more later too. The third group is, this is what I think of as the real rocket science type of stuff, right? Guidance and navigation control and the entry, descending, landing sequence. On Perseverance, we cheated. We stole the code from Curiosity to do this. But we made it better though. Our descent was more controlled. For Curiosity, they were kind of counting on just a lucky roll of the dice to not land on a big rock or something. Perseverance actually had a camera looking down and scanning the terrain and looking for the best spot to go, and it would steer its way into that spot, and it looked like it worked very well. Systems is the last group. This is the group I'm in. We do power, thermal management, communications, redundancy management, fault protection, file system, I/O interfaces, timekeeping, that sort of thing. I personally spent most of my time working on thermal management and control. There are over 300 heaters on the rover, and it was my job to make sure each heater is keeping its zone at the right temperature level. Another thing I got assigned was the alarm clock. And one day I was kind of complaining to my boss about, how hard can the alarm clock be? I mean, I was hoping for something a little more prestigious. And he went up to me and said, dude, the alarm clock might be the most important module in the system, because if the rover doesn't wake up, mission's over, right? So that made me feel more important, and then it made me feel terrified. But so as far as our software development process goes, it's similar to a process that tries to meet DO 178 objectives in the aviation industry, so airliners and that sort of thing, what I used to work on. The code runs under an operating system called VxWorks. It runs on a computer called the RAD 750 made by BAE Aerospace. It has the PowerPC processor on it. These processors, they've got about as much power as you remember those old green and purple Macintoshes from 20 years ago? Yeah, it's about like that. We would love to use modern processors with a whole lot more horsepower, but the density of the logic gates on those things make them very susceptible to radiation, and they just are not going to be reliable in space. So we have to put up with the slow, old style processors. There are actually 3 RAD 750 computers on the rover. 2 of them operate as a redundant pair, and a third one is dedicated just to image processing. That's all it does. And in fact, earlier I mentioned the descent as it was scanning the terrain. That third RAD 750 was used to process those images. And that computer will continue to be used to process images on the ground as the rover goes about its regular scientific activities. The code is cross-compiled with the VxWorks compiler on Linux servers. Our desktop clients, some of us use Mac, some of us use Windows. I happen to use Windows. I don't know if it's any better. We use various different integrated development environments to write the code. Wind River is the company that makes VxWorks, so they have a tool called Workbench. Some people use Emacs. I'm really weird because I actually take the code and import it into Microsoft Visual Studio just because I like the editor so much. The code is written in C. But we try to auto-generate a lot of that code using Python scripts, and we feed those scripts XML files for input. These XML files are usually long lists of devices like heaters and switches and thermal zones and things like that. It cuts down on the probability of errors if we can automate this stuff, treat each device, logically in a similar fashion. The software is it's divided up into about 150 separate modules. Each discrete functionality we try to put in its own module. So like power has a module, thermal has a module, um, the uh, like the instruments, RIMFAX and MOXIE, they each have modules. There's a whole module just for raising the mast. The mast is that post on top of the rover, the head, basically, where the cameras are. That is being risen today, actually. Um, and once that mast is hoisted up into place, it locks mechanically and it cannot be lowered again. So I just think it's interesting. There's a whole software module that will be executed exactly once and never again. The code is compiled into, believe it or not, one giant executable file, which has all the functionality in it. It's about 20 megabytes. Curiosity used this one file for both cruise, entry, descent, and landing phases of the mission, CEDL, and for surface operations. We're running out of resources on this platform, so for Perseverance, we created two separate executables, one that runs during cruise, entry, and descent, and one that runs on the surface. So the surface version, of course, does not have any of that code for guidance, navigation, and control, or the entry, descent, and landing sequence. Likewise, the cruise software does not have a lot of code in it for operating, say, the drill or the arm, for example. The hardest part, in my opinion, of writing software for the rover is testing, because I can't do it. I can't run my code on the rover. The rover, I do not have access to it. And even if I did, the tests are kind of limited because the rover does not behave the same way on Earth as it does on Mars. The gravity is different, the temperatures are different, the air density is different, and you can only use a vacuum chamber so much. Um, so we do have teams in Atlo that conduct software tests, but as developers, we do all of our testing in three different ways. We use software simulations of the spacecraft. We have a system called WISTIS, Workstation Test Set, that emulates the spacecraft, and we can run our code on that. We do a lot of unit testing of functions. Those unit tests are written in C and they run on Linux. And we have some flight hardware in the lab so that we can run the code on them, on those computers. But they aren't necessarily connected to anything meaningful. They aren't connected to the rover, so we can't manipulate the arm or turn on heaters or anything. The way we get the code onto the rover, first of all, we always intend to land with the same software that we loaded onto the rover when we took off. And I think this time we actually did it. In the past, they have uplinked a new version of the code to the rover before it landed, and they landed on the new version, a different version than they took off with. But this time, I believe they landed with the same software that it had when it took off. The way we communicate with the rover and send it new builds of the software. So everybody knows there's a lag. The speed of light is a real limit for us. So there's between 3 and 22 minutes of time to passes to send a signal from Earth to the rover. And that's actually the best case scenario. It's actually worse than that because communicating directly to the rover is slow and error prone. So what we usually do is communicate through satellites orbiting Mars. So when we want to send a command to the rover, we send it from our deep space network on the ground at Earth to a satellite that's orbiting Mars. Then that satellite moves into position over the rover, downlinks that command to the rover. The rover processes the command, but it probably can't get a reply off while the satellite is still over it. So it has to wait for the satellite to make another revolution around the planet. And then the rover can uplink to the satellite, and then the satellite has to move to a position where it can see the Earth, and then it downlinks the data down to Earth. So it's a complicated ballet of things that has to happen in order for us to communicate with the rovers. So due to this complexity of communication, we try to plan activities on a daily basis. Each day, the rover has a plan set out for it. We can't call it a day on Mars, though, because a day is 24 hours and a Martian day is 24 hours and 37 minutes. So we call it a sol. Uh, 37 minutes it doesn't sound like much. It's just enough to be really inconvenient. But as the rover is performing its activities, it creates these data products. These data products can be information from the instruments or diagnostic information about the rover itself. At the end of the sol, the data products are downlinked back to Earth through the satellites. That data is analyzed by the scientists, and they devise an activity plan for the next sol on Mars. That usually contains objectives that the rover is trying to meet, whether it's a science experiment or driving to a particular place or that sort of thing. So that plan is uplinked from the DSN to the satellite, and then relayed to the rover. The rover carries out the plan, and then it sends its report for the day when it's all done. And that report, those data products, they arrive on Earth a little bit later each day because the Earth day and the Mars day are a little bit out of sync with each other. And there are scientists, especially at the beginning of the mission, who live on Mars time. So they're working at 3 o'clock in the morning, and then they're sleeping at noon the next day or whatever. That I think eventually people switch back to Earth time, though. It's just too hard to live on Mars time. And so I think what a lot of the scientists do is they just stay late a little bit later each day and wait as they're waiting for that data product to come in. And then at some point they decide, okay, this is it. I'm just going to come in early the next morning instead. So every couple of weeks, I think you get this resyncing where the rover has a few extra hours of time to itself, which it probably spends asleep. The rover spends an awful lot of time asleep. People don't maybe realize that it's only awake for 3 or 4 hours a day, and that's due to power. The power supply for the rover, like I mentioned earlier, is the RTG. It puts out about 100 to 110 watts of power, which is barely enough to run all the computers. And to give you a sense of scale, that's about the same amount of power used by an old style incandescent light bulb. So you have this vehicle that's the size of an SUV. It weighs 2,300 pounds. It drives around, it shoots lasers, it drills rocks, all using the power of one light bulb. So the way we are able to allow that to happen is there are 2 lithium-ion batteries in the rover as well, and combined, those batteries, I think, can put out 500 watts or so. So we have between 500 and 600 watts when the batteries are charged in order to do that enable us to do all these activities. But it takes a long time to charge those batteries, so it spends a lot of time sleeping. There are no solar panels on the rover itself. There are solar panels on the helicopter, but not on Perseverance. So we depend on that RTG. But all of this complex time management that's involved with the rover and the fact that we have such a difficulty communicating with it in real time means that it's very important that the rover do as many things as possible autonomously. And Perseverance is more autonomous than any rover in the past, and it's capable of making decisions now. In other words, if it has a choice between 2 different scientific experiments it wants to perform, it will choose the better of the 2 in the time that it's given. If it's doing something and it discovers, an interesting rock or something, it may be able to schedule that on its own rather than asking Earth constantly, what should I do? What should I do? What should I do? That really wastes a lot of time, that sort of thing. When we don't want the rover sitting idle on Mars because we know we have a limited amount of time. So let's see, we have rolled out. This is the Atlas V rocket, and the rover is tucked up inside that payload fairing at the top there. This is launch day on our way to Mars. This is the control room at JPL. This was during launch, not landing. This happened back in July. You can see everyone is wearing masks. JPL, like many organizations, has been on mandatory work at home since last March due to the COVID-19 pandemic. And it has taken some doing to get used to working this way. Um, but I think JPL is handling it quite well. In fact, you could think of JPL engineers as the ultimate remote workers anyway. Our systems that we work on are deployed hundreds of millions of miles away. So working remotely, in a sense, is not new to us. Um, Working from our homes may be, though. Um, in fact, the Curiosity team, they're still running operations. Curiosity is still up there working, and they are doing operations from their homes. The Curiosity team and the Perseverance team are actually two separate teams of people. There are people that have been on both, but for the most part, they handed off their code and their design to us, and we took it over and created another rover. So we don't really commingle all that much, really. This is my ridiculous setup at my house, our spare bedroom. I'm trying to get down to two computers, really. And that's my telescope in the background there, which was more useful when I was living out in the desert than in Los Angeles. But, when I first understood that I was going to be spending a lot of time working from home, first thing I did was I went out and bought the best darn office chair I could find, which is the Steelcase Leap. So, and it's made a huge difference in my life, really. Thank you, Steelcase. So I eventually got used to working at home, and there are some advantages to it. And I started to think, this isn't so bad. And 2020 has been a rough year, but things are looking up, and we're on schedule to Mars. Things are going well. So it's going to be smooth sailing from here on out, is what I thought, at least. And then the fires hit us here in Southern California. This is the Bobcat fire. This picture was taken from Monrovia, California, which is just a little bit east of where I live, on the eastern edge of Pasadena. Uh, this the fire looks scary in this picture, but I'm telling you, when you're standing there, it's not the flames that are scary. It's the smoke and the ash that's raining down from the sky because you cannot breathe. And my wife has asthma, and so we knew we were going to have to evacuate the area. We were scheduled to go on vacation actually in Big Bear, California. We had rented a cabin there. So we thought we would just wait it out in Big Bear and come back after the fire. Um, I coined a new word. I call it the evacuation. So that's where you're trying to flee from impending doom and take a vacation at the same time. So we got all settled down in Big Bear at our cabin, and then this fire, the El Dorado fire, hit Big Bear. So we had to head back to Pasadena. And at this point, it was pretty clear that I couldn't stay in Pasadena. I was going to have to take my computers and work on Rover code remotely yet again, more remotely than I was before. So we knew we had to leave the area. There were just fires all over the whole western half of the United States in the summer of 2020. It was really pretty concerning to me. Hotels were filling up, and you can't fly anywhere due to the coronavirus. So we knew we were going to have to pile into the car and head out somewhere. I have friends and family in Colorado, but they were on fire too. So, of course, the only logical thing to do was to head off to Michigan. So we took off and started driving, and we settled down at my mom's house in Grand Rapids, and we all set up about 5 laptop computers in my mom's house. And my wife connected to her real estate business in California. My 3 daughters were doing remote school through their school in Pasadena with a 3-hour time difference. And this is how JPL engineers telework. I don't personally send commands to the rover through these antennas, of course, but this is how we communicate with spacecraft. All of the spacecraft beyond about the moon really go through this network of antenna installations. This is a service we run for the whole world, by the way. not just NASA, but many spacecraft that are out in the solar system communicate through these antennas, and all that data comes back to JPL here in Pasadena. These antennas are spread out across the world in 3 different locations at equal angles, so that as the Earth rotates, so we always have an antenna that we can point to the spacecraft. The upper right is in the Mojave Desert, Goldstone, California. Lower left is Madrid, Spain, and the lower right is Canberra, Australia. If you want to see what these dishes are talking to, go to eyes.nasa.gov/DSN. It's really cool. You get a real-time view of all the spacecraft that these antennas are communicating with, and there's dozens of them too. It's really, really amazing. So I'd like to talk about a little bit of rover trivia back here in Pasadena. Perseverance has a twin brother named Optimism. We keep it in the garage behind the Mars Yard at JPL. Mars Yard is an area of the facility that we have tried to make look like the surface of Mars to do mobility testing. So they brought in rocks and created hills and things so that we could drive in a simulated environment and see how it works here on Earth before we do it for real on Mars. The funny thing to me about the Mars Yard, there's a lot of places in Southern California that look remarkably like the surface of Mars, but Mars Yard isn't one of them as far as I'm concerned. It just looks like Pasadena without trees to me, but it's functional. It does the job. So that Sky Crane landing system, speaking of the Mojave Desert, this is how we test that. This is a landing radar test that was done for Curiosity. Another bit of trivia here, we put a plaque on the side of the rover kind of at the last minute to honor all the healthcare workers that have been so amazing over the last year. I wanted to talk a little bit about the wheels on Curiosity. It's been roving around now for 10 years. And yes, we've got some wear and tear on it. One of the things I think is kind of fascinating about this business is things that seem obvious in retrospect, I guess just weren't at the time. So we've got some holes in the wheels now, and it turns out that the rocks on Mars are really sharp and jagged, which makes sense, right? There's not the same level of erosion that you would have on Earth because the air is so thin and there's hardly any water. So yeah, so we've got some holes in the wheels. This does not affect Curiosity's ability to carry out its mission, but the operators now try to drive around rocks rather than over them, just so we can keep the amount of damage accumulating minimally. And if you look at the back of the wheel there, you'll see some other holes. Those are intentional. Yes, those do spell out JPL in Morse code on the Martian surface. There's actually a practical reason for that. They call it visual odometry. If you take a picture of the tracks that the rover leaves behind it, you can measure exactly how far it's traveled by using those marks, and you can also tell if the wheels are slipping or not. However, Perseverance does not have any holes in its wheels, and I think that we have better methods now for computing that kind of thing. Also, I think NASA headquarters prefers us not to put advertising on the wheels. So this is yeah, the wheels are now stronger. They're made of aluminum and titanium. They're thicker. They're a little bit narrower, and I think they're a little bit taller too. But we expect them to hold up very well now. Let's see, got some time for some more trivia here. One of the neatest things I think about these missions are the pictures. I think everybody loves the pictures, and our ability to get better pictures is improving all the time, and that's really exciting. There are 23 cameras on the rover and 2 microphones. So we should get some sound too. It will sound a little strange because of the density of the Martian atmosphere. Sound will travel slower. It'll be quite attenuated, but it'll be interesting. The Mastcam Z, I think those may be the best cameras as far as for humans, for human eyes. They may produce the best pictures. Curiosity had Mastcams, but no Z. The Z stands for zoom. It's an optical zoom feature. The Curiosity, they wanted to do the optical zoom on Curiosity, but they couldn't quite get it done in time. So it launched without the optical zoom feature, but Perseverance has it. So we should be able to get some really nice pictures. Now, a funny story about remember that picture of the rover guts with the wiring. The one set of cameras, I can't remember if it's nav cam or has cam, but somehow the left camera got plugged into the right port and the right camera got plugged into the left port. And this was discovered after it was too late to go back and change the wiring. So for a little while there, the rover was cross-eyed, and there were a lot of meetings about how we were going to fix this problem. And they came up with some wacky ideas like special wiring adapters and things like that. But of course, the correct solution is to simply switch the images in software. So flight software to the rescue. Once again, we made the left camera the right and the right camera the left in the software, so it's no longer cross-eyed and everything is fine. And I have a few minutes left. I think at this point we can just go to questions.
Okay. Let me come back. Thank you very much. Very interesting. We do have a few questions, although you were doing something that was annoying to a lot of people, which was answering the questions before they had a chance to ask them.
I love questions though. I mean, because I'm somebody always brings up something I didn't think of.
Yeah, no, this should be fine. Just for everybody out there, either raise your hand or add more questions. I've got the ones that came in during Steve's talk, so I can ask a few of those. One of them was, speaking of the helicopter that's with Perseverance, Ingenuity, how does the helicopter communicate with the Earth? Also, does it have a finite life? What are the limiting factors determining its performance life?
Oh, good questions. The helicopter only communicates with the rover base station. It cannot communicate with Earth. So it sends its data directly to the rover, and the rover sends commands to the helicopter. The helicopter's lifespan, yes, it's definitely limited, mostly by batteries, I think. The big challenge with the helicopter is temperature, because it gets really cold, 140 or more degrees below zero. So the battery on the helicopter is amazing. It actually spends most of its power just keeping the thing warm. And it can only do that for so long. Let's see. What was the other part of the question?
Limiting factors.
Limiting factor. Yeah. So, and speaking of that, so thermal concerns are very they're very concerned about that. They need to keep the thing warm. However, they also needed to keep the weight of the helicopter down as low as possible because, for obvious reasons. So there's this stuff that we use in the aerospace industry called Aerogel. It's an insulation and it's super light. The stuff practically floats in the air. And they considered insulating the helicopter body with that, but they decided not to because it's too heavy. So we expect the helicopter, in a month, maybe two, to make its flights, and beyond that, I'm afraid its life is probably going to be over after it makes. Hopefully, it will make at least one flight.
Oh gosh, hopefully more. Catherine in the audience has her hand up. I'm going to ask her to unmute and she can ask her question.
Hey, Steve, this is Catherine and Andy, and we're so excited to watch this. And now I can't remember my question. I had originally was going to ask about DSN, but then you pre-answered it. And so then I was wondering, in the title of the talk on the posters and stuff, it said about perseverance to adversity. Was it adversity a name, or what was that?
Oh, no, it's just, it was actually NASA made me change my title. My presentation got rejected 3 times by NASA bureaucracy for various problems. And my original title was something like like desperation and hopelessness, rejected names of the Mars 2020 rover. So no, my title just was meant to address the fact that it's difficult enough to work on a mission like this during normal circumstances, but when there's a fire in your backyard and people are dying of a pandemic, it's even more challenging.
All right. Another question. Somebody asked another Steve, when will the EDL video be released?
Oh, good question. I'm looking forward to that myself. I'm hoping next week. Yeah, so if you don't know, we had cameras on the back shell and various parts of the rover just to film the entry, descent, and landing sequence. And if that all worked well, then we should have some really nice video of the landing itself. It takes a while. We have a lot of other higher priority things than getting fun video back from the rover. But if we get it, I think it would be really neat. The big problem with that is bandwidth. I think we have our bandwidth kind of peaks at about 2 megabits. So if it's, we have hundreds of megabytes of this video, and I'm not sure how they're going to work in the telemetry data stream to get all that data down. It's like pushing a swimming pool's worth of water through a garden hose,
Another question had to do with the helicopter on Mars, and this is actually from Glenn, and he and I were kind of having a civilized discussion about what it meant to have powered flight from the surface of another planet. But he said, what about wind on Mars? Will that affect the helicopter?
No, it's too thin. The air is simply too thin. It really won't affect the helicopter. In fact, I love that movie, The Martian, with Matt Damon. Matt Damon is sort of our hero at JPL. He hates it. But there's a scene in that movie where the rocket ship that landed on Mars is it looks like it's going to tip over in a bad storm. And that's not realistic. The wind, you can hardly feel it because the density of the atmosphere is so thin. So you would never be able to knock anything over as heavy as a spaceship with the wind. And the author of that book admitted that was a mistake too. But no, the big problem with the atmosphere is the dust. And the biggest concern that the helicopter team has is dust. When you have rotating blades of a helicopter, it kicks up all this dust. You can see that on Earth, and that dust kind of tends to go up in this cloud and come back down again. And so they're worried that the dust will settle on that solar panel, and then at that point we will have a lot more trouble charging the battery, and that could put an end to the helicopter prematurely.
Okay. Could you tell us a little bit more about your alarm clock? Is it working? Did it do what it's do yet?
Well, okay, so I did most of the code that I wrote is actually in the Surface version of the code. So we need to switch over to that version. I don't think they've done it yet. And so what the alarm clock does is it wakes the rover up. We in order to charge the batteries, everything needs to be shut down except for some heaters. So my job is a little unusual because I work on code that runs when the computer is turned off. You might be thinking, well, how's that possible? Well, we kind of cheat. There are other kind of smaller computers that I can use the main computer to program the little ones. And so when the main computer is sleeping, the little ones take over and they power on heaters to keep the rover warm at night. And it also runs the alarm clock. And when the time is right, it sends a signal to the power module, which powers up the main computer, and then the main computer takes over. But I'm not exactly sure when we're going to switch over from the Kroese version of the code to the Surface version. There's so many checkouts and diagnostics and everything that have to happen.
Okay. Another question. What would be a definitive proof of life on Mars, and what would be enough for us to get excited?
Wow. Yeah, I'm not a scientist, so I'm an engineer. So I'm
sure some of the engineers.
I will tell you this. This is what the scientists tell me. The reason we picked Jezero Crater to land on is because it's a river delta. Like think of the Mississippi River down by the Gulf of Mexico. That's where all that water drains down into, and we know absolutely for sure that there was water in Jezero crater. Because it's very clear that what we're seeing there is the exit of a large river that ran down through the mountains. So rivers always deposit a lot of sediment at the bottom, and they are hoping to examine this sediment to find little bugs or whatever, right? So that's my engineer's explanation of a scientific goal.
I just looked up Jezero a little while ago, and it means lake in Czech.
Oh, I didn't
So,
know that.
yeah, so I thought that we thought it was named after somebody. I had to check it out. So this is kind of a combination of two questions. I was curious. I think your style of presenting your life at JPL is fascinating and very appealing. I was going to ask if you are going to write a book or start a podcast. Another person wanted to know what's next for you at JPL, the next project that you'll be working on, and if you're going to be working on the Mars sample return.
Oh, those are good questions. I don't know about the book. I'm not much of a presenter or public persona, so I'm going to defer that question. But my next project is actually Psyche. I'm working on it now. There's an asteroid out there called 16 Psyche, which is a giant metallic asteroid. It's been in the news a couple of times. It's the one that everybody says is worth $5 quintillion or whatever because of the amount of ore and gold and silver and stuff in it. It's kind of sad that the only way we can think of these amazing solar bodies out in the solar system is by assigning a dollar amount to them, but that's, I guess, what gets the headlines. So I'm working on software for a probe that will launch in a couple of years that will explore that asteroid. And that program is kind of neat because we're going to do two things on that spacecraft that we haven't really done before. One is it will be powered with a solar electric ion plasma thruster, which kind of in a way sounds more impressive than it is. It generates a very, very small amount of thrust, but it can do it for a very long amount of time. And then the other neat thing about it is that instead of using radio waves to communicate with Earth, it will use a laser beam, which should up the bandwidth by about a factor of 10. We'll still use radio, but the laser is a technology demonstrator again. And that's kind of a neat thing to work on. After that, I do hope to get onto the Mars sample return mission, where we will. So Perseverance is going around, will be going around picking up samples and caching them. And the Mars sample return mission will be a mission to go and pick up those samples and bring them back to Earth. That'll probably be my last mission before I retire.
Another person wants to know, is any of your code or open source? And do you use any open source products in the flight software?
Not in the flight software. We use a commercial operating system called VxWorks, and the code is not open sourced. Yeah, we do use a lot in our development, though. We use Linux a lot. And we have other various open source software. So in the development process and, in the analysis of data and just as general productivity tools, we do love open source software. And I think there are people that at JPL that contribute to the open source community as well.
Okay, and I guess we're getting close to wrapping up here. I wanted to ask you finally, is there anything you want us to pay attention to or be on the lookout for in the next week or so with Perseverance and Ingenuity?
I think, the pictures will be amazing. I think that I'm not a scientist and most people aren't scientists, so we get a little bit befuddled by all the data that comes down from these instruments. It would be interesting, though, to take a look at what they're actually finding with these instruments that use, X-ray spectrometers and things like that. Let the scientists look at that data, and they have some interesting things to say about it sometimes that tends to go over my head.
Well, I just want to say thank you very much. This has been fantastic. And so thank you for your expertise and your energy and your humor. It's been a great presentation.
Well, thank you.
Just wanted to bring everybody's attention to the feedback link for the survey in the comments and let you know that what's coming up next is our special effects science fiction art panel, which is going to be really exciting. Once again, thank you so much, and enjoy the weather that I'm assuming is beautiful.
It is beautiful. I still remember what it's like in February in West Michigan, though.
It's beautiful. Good luck.
Thanks, Steve. Take
Thank
care.
you.
Thank you, Steve.
We're going to shut it down, everybody. We'll